A2 by 2 sigma square, 2 sigma 0. That means equivalent I can say I can maximize A1 minus A2 whole square by sigma 0 square. Okay. So, now this is the, if you remember that this is the difference of the, earlier we talked about that we were trying to do that in the max filter explanation we were talking about we were doing the sigma 0 square ai square capital T by sigma square. Now instead of doing that I am taking a different signals energy, different signals power and this is the noise power. Okay. So that means this is the difference of the desired signal component at the filter output. Okay. So now that this let us see, that means we are in that case, that means it will be that the S by signal to noise ratio will be A1 minus A2 by square by sigma 0 square. So when it was, what was the maximum value, if you remember, that was 2E by N0. But here, when I have taken a difference component, then actually it will be the different signals energy, 2ED by N0. Now, what is my ED? ED was the different signals energy. That means 0 to capital T and S1 minus S2 whole square by whole square dt. Now, if you play with this thing, that means if I maximize this one, that means this ED, this my that means now if I do this, then what will be my probability of beta error? Probability of beta error, if you can remember, that probability of beta error was Q of A1 minus A2 by 2 sigma 0. But I know that means if I A1 minus A2 by sigma 0 is root over of 2ED by N0, now divided by another 2, that means ED by, if you can remember, that means A1 minus A2 by sigma 0 is, you can remember that, say from this expression I can write A1 minus A2 by sigma 0, that is equal to 2 ED by N0. Now, what is my probability of beta error? Probability of beta error is A1 minus A2 by 2 sigma 0. Now, if I do the 2 sigma 0, then I have a half, then basically you are removing this, you will put here. Okay, ED by root ED by 2N0, that means Q of root ED by 2N0. So this is the case. This is the maximum. This is the minimum probability of beta error. Okay. Now this one, that means this one is that means energy of different signal at the filter input. Okay. So that means now let us do this. Let us define that. Let us play with this one. Okay. So let us define a cross correlation between two signals. That means I know that S1T is, that means both the signals, for logical 1 I am sending S1 and for logical 0 I am sending S2, two pulses, and I am defining the cross correlation between S1 and S2. That means then what is the cross correlation? Integral of 0 to capital T S1 T S2 T dt divided by the 1 by, if you can remember, or rather I can say that 1 by root EB by 1 by root EB. If you have studied that correlation, means probability stochastic process, you will see that this is the basic definition of the correlation. Okay, rather it is the normalized correlation. Rho is between -1 to +1. Okay, and you see that, and that as it is -1 to +1, I can also define that rho as cos theta. So that we have studied in probability stochastic process. That okay, that means covariance divided by sigma 1. If you remember that rho equal to cov of x and y divided by sigma x sigma y. that if you remember that sigma x into sigma y, that is basically, they are basically same, that is equal to sigma, that is equal to sigma square. That means that if sigma x equal to sigma y, I can drop this suffix x and suffix y, and I can say this is sigma square. Now what is my, that signal sigma square, please remember. Okay, now signal sigma square is basically, if you play further with it, that you will find that it will be that EB, and we will find that, like here that what is that code? Actually, we will find that EB into EB. EB basically will get a power, and here we will have 1 by some t integral of that S1 t S2 t. We will basically get this. S1 t is, now the t into PV is EB. Okay, and this is 0 to t S1 t S2 t. So this is the row, and this is between -1 to +1. Okay. Now if I define this S1 t as my signal vector and S2 t is another signal vector, then I can define, I generally, sometimes we write S1, please remember that sometimes we write S1. Sometimes we say, that is, it is a function and t 0 to capital T. Sometimes we just write this one as some signal vector. And S2 is another signal vector. And this is these two vectors cross correlation you are doing. Okay. Now what is my difference signal? The difference is signals energy. Difference signals energy was, if you remember, that S1t minus S2t whole square. Okay, square dt integration 0 to t. Now if you play with it, then S1 square S2 square minus 2 S1 S2. Now what about this term? This term is basically, I have just proven that rho into EB. Okay, so I have, and also that individual one is that S1t and S2t, that I have defined that S1t I have sent for logical for 0, and that logical 1, I am assuming that for logical 0, that I have chosen that S0t and S1t and S2t in such a way that they are of equal energy. That means equal energy means that, say I have defined S1t something like this. This is capital T. This is my S1t, and my S2t, say I am defining, this is my S2t, and if you just, this is my T by 4, this is T by 2, this is 3T by 4, okay, and say this is your, say, 1 volt kind. This is also the same thing, but that is -1 volt. So then you will find that this is for logical 0 and this is for logical 1, say. So then in that case, the energy of the individual signal, that is S1t and this is S2t, that will be same, because energy is basically this one and energy is basically this one. Okay. Okay, this is T equal to T. So I can choose that EB equal to EB plus EB minus 2 into rho into EB. That means 2 into EB 1 minus 2. Okay. I can just write it 2 EB 1 minus 2. Now what about this probability of beta error? Now probability of beta error in terms of this difference energy, I am just breaking it into the individual symbol energy. That means that EB, please remember, for logical 0 you are sending the pulses, that pulse energy. It is though if they say that it is a bit energy, please remember this term. Energy associated with a bit, it is not bit. So that means energy associated with a bit. That means 0 you are transmitting by some 0 to t by this pulse. Okay, so this is say S1t. The energy of this S1t is my EB. Okay, now if I just express this ED into with some associated bit energy, then you will find that QEB into 1 minus rho divided by N0. N0 is my power spectral density of the noise. Okay. So that AW power spectral density of the AWGN noise. AWGN noise, if you remember that my power spectral density is flat N0 by 2. Okay. If you remember that P of F, that is the power spectral density. You see, this is the power spectral density. This is F of the white Gaussian noise. Okay, it is any white noise power spectral density is flat. Okay, with respect to frequency, and this PF is not power. Please remember, this is watt per hertz. Okay, this rather will say that PWF. Okay, and what my total power? P is basically minus infinity to plus infinity. PWF. Okay, watt per hertz. Hertz then is watt. Okay. So this we have explained. Now say I will choose S1T and S2T, so that I will see if I choose S1T and S2T in a different way, your rho will be different. Now if you see, that means if I choose my S1T and S2T, they are anti-correlated over a symbol time. Please remember this, anti-correlated over a symbol time. Anti-correlated means say rho equal to minus 1. Rho equal to minus 1. When can it be rho equal to minus 1? Say I can choose some S1T and S2T. That means rho equal to minus 1 means I have just drawn the picture. That if you remember that rho equal to minus 1 case, can you say your ST means S1T is plus A and S2T is minus A. Okay, so so that means in that case I am choosing my signal for say some T. This T, say S1T is something like this and S2T is something like this. Then this will be anti-correlated signal. Okay, or I can choose this capital T. I am choosing this is A and for S1T, and S2T is minus. Okay. This is S1, this is this. In that case, you will find that your value of rho will be always minus 1. Okay. So that means this is anti-correlated signal, and in that case, that rho will be minus 1. Now when rho is minus 1, then it will be PV equal to 2 square Q of 2EB by N. Okay. That means Q of, when rho equal to minus 1, Q of root 2EB by N0. You see, this is S1 is a vector. See, this is a vector kind of thing. This is not S1T, and this is S2 another vector. That means I am just defining that S1 is maybe like this plus A and S2 is T, this is ST, this is S1T, this is S2T, this is plus A. Okay. Now okay, and why they have written root EB? Because what is this signal's energy? Energy is A square into T. So they are choosing just they are writing this amplitude is something, say they are assuming capital T equal to 1, and they are choosing the amplitude, rather if they choose energy is basically A square if capital T is 1. then I can write it as that ambiguity is something like that. That they are right. Okay. Anyway, so this is for that means that detecting antipodal signal with a matched filter. Okay, that we have studied. Now, if two signals are orthogonal, that means that vector S1 and vector S2. Vector S1. So that means what is the case? That means say this is my T, this is my T by 2. Now S1T is say this is some 1, then after that 0. Say this is your T by 2, and S2T is past 0, then okay. So then if you see that if you take the integral of S1T S2, that means this is my S2. Okay. Now orthogonal means that means I am saying rho equal to 0. Rho equal to 0 means these vectors, that means if you will remember that rho is basically cos theta, that is theta with rho is 0 means theta equal to 99 between the two vectors, and that means that rho equal to 0 means 1 by EB integral of S1 T S2. If I just do the integral of S1 T S2 T, you will see that this is going to be 0. So if you choose your S1 and S2 in such a way, then you will have what about if you choose this way, and what about probability of beta? Rho is your, here the rho is 0, that means rho 0 means, that means EB by Q of root EB by Ng. Okay, now you have this Q of root EB by Ng. So that means in the previous case, please note that in the previous case you have PB equal to Q of root 2 EB by root 2 EB by N0, here it is root EB by N0. So that means in this case your argument Q of this one is bigger than the previous one. Now when that the argument of Q function is bigger, the probability of beta is less. Okay, so that means if you, for the same thing, if you choose the S1T and S2T judiciously, that means in this case, if you choose your S1T, S2T in this way instead of orthogonal one, then your probability of beta will be much minimum, because it is a 2 into EB by N0 Q of, and here it is EB by N0. Okay, so now that means let us talk about this max filter detection with the antipodal signal. Okay, that means antipodal signal means if you can remember that this is my, just I have explained that this is my S1T and this is my S2T. So that means the antipodal signal means rho equal to -1. Now that if you remember what will be the Q equal to some 2 EB by antipodal signal, Q equal to Q of 2 EB by N0. Now what about this N0? N0 here is given 10 to the power -12, 2 into EB. So that means EB they are calculating, that is d square T dt. That means basically you have to do the, you have to take the this means 0 to 3. First of all, this is each one is 1 microsecond. So that's why 10 to the power -6, 10 to the power -6, 10 to the power -6. Each one is millivolt. That means 1 millivolt, 10 to the power -3 whole square. Then 2 millivolt, 2 into 10 to the power -3 whole square, and then again 10 to the power -3 whole square. So that means energy is something like that. This much 6 into 10 to the power, that means 6 into 10 to the power -12 joule. Okay. Now EB means 2 into EB, that is 12, 10 to the power -12 by 10 to the power -12. So that means Q root 12, that is Q 3.46. Now if you have a normal table, then you will see that I will have a, sorry, this is not that. Okay, so I will check the area, that is Q of 3.46. That means say this is your, because this is 0 to 1 standard normal variate, this is your in 0, 1. Okay, so somewhere here will be 3.46 if you can remember. Then this much area, that is very low probability. Okay, because 3 means within -3 to +3, your 99.78% area will be covered. That means 1 minus that 0.9978, that will be the Q 3.46, something like that. Okay, that means some very low probability. Okay, they have calculated. Q is 3 into 10 to the power minus 4, the probability of synthesis. Okay, or probability of symbol. Okay, now also you can see there are certain when Q is greater than 3, you will have to see. This is very important because once the argument of Qx is greater than 3, you can remember that is if that Q of x, if that x is greater than 3, we need not calculate this area. Actually, there we can do the direct approximation. That means that if you see that is from the normal table, you are getting 3 into 10 to the power minus 4, and if you use the approximation, it is 2.9 10 to the power minus 4. That is their approximate this. What is the approximation? If you can remember, for x greater than 3, this qx can be directly written instead of this big formula. I can write it as that just there is no integration. This is the important thing. That 1 by x to 2 pi. So that means if you have some say 3.2. So that means you can directly put e to the minus 3.2 whole square and something e to the minus 9 by 2, something 4.5 e to the minus 4.5, 1 by 3.2 directly you will get something. Okay. So but here as there is integration, then it is difficult. You have to check the calculator. Okay. But please remember this is valid for x greater than 3 for standard normal. So that they have done the approximate relationship as x was greater than the argument of qx, that means which is x greater than. Okay. Now that now if I have a say error performance in case of binary signal. That means when I am doing a unipolar signal. Unipolar signaling means for binary 1 I am sending class A, and if it is binary 0 I am sending it is or logical 0 I am sending S to T, I am not sending any signal. So what about this? What if I choose this type of signal, what will be the value of rho? Okay. If I take the vector representation S1 and S2 bar, if you see that with integral of now, first you have to check the value of rho. In this case, the value of rho will be 0. So that means these sometimes are orthogonal kind of. Okay. Say you can say this is my S1 vector, this is my S2. Okay. Okay. And what will be and they have chosen that actually signal is it is like that 1 0 0 1 1. They are transmitting. Okay. So your binary signaling SIT will be like this. And what will be the what you will do? That means this is your SIT and RIT and all these things. That means you are sending is. If you can remember, this is my SIT. Now what is my RT? If you just let yes, this was your SIT that you have seen. That means then after that most probably it is 1 0 0 most probably 1 and maybe 1. I am not very sure. Okay. So this is your that means you are sending this is your signal and then AWGN, then you have a RT, there is no frequency down conversion, you have a max filter, finally you are getting here the jet and you have to take the decision at the please remember means this is some sort of a this is that SIT is a transmitted waveform, that is it is coming through the channel, at the channel it is the noise and at the receiver you are getting this RT. Say I am assuming there is no down conversion. Okay. So now with this RT, when I am doing this max filtering, that means my reference signal, I am taking S1T minus S2. Okay, so I am doing a different signal switch. Now S1T minus S2T is A, because S2T is 0. And then I have a correlator structure 0 to capital T. Then I have ZT, Z with, please remember, this I am doing capital T. Okay, because that is the max filter correlator structure. If you can remember, that means that what was my max filter correlator structure? That I have to do the integration up to capital. This is my correlator structure. See, this is the standard match filter. Okay, say match to S1 minus S2, sometimes match to ST. Match to S1 minus S2 means actually you have to do here the S1 minus S2. Okay, please remember here it is 0 to T and all these things. When it is correlator structure, then because you are doing the sampling, that means here you have to put capital T. If you can remember that what we did in the correlator structure, that see this was my ZT and you have put that T at T equal to capital T. At T equal to capital T, finally you have defined that Z of capital T. Okay, so that means we are doing the correlation at up to T equal to capital T. That we are doing. Okay, so that means 0 to capital T, and then you are getting the ZT. Okay, now this we are getting Z of capital T. Now, so, and this Z of capital T, you are checking that whether it is greater than gamma 0 or less than gamma 0, and depending on that, you are choosing your whether it is S1 has been transmitted or S2 has been transmitted. If S1 is transmitted, you know that it is a logical one. If S2 is transmitted, you know that it is logical. Okay, so now if you just do this thing, if you can remember, that means finally what will be the probability of beta reduction. Now you see that when you have chosen this S1T and S2T in this way, they are orthogonal. They are orthogonal. The probability of beta will be root EB by N. Q of root of EB by, if you can remember, Q of what? EB by this root of EB by N. You see, that means I am not explaining this thing. You can just play with it a little bit. You will find that okay, how they are calculating A1T and all these things. And finally, you see that the beta transformation, it will be Q, because they have done all this. Please read those things. That finally, as I know that they are orthogonal, it will be like Q of root EB by N. Okay, that they are doing. Okay. Now with this one, but if I, so that means basically this is the figure of merit. What about your probability of beta? This is basically a figure of merit. Okay, for getting this one, they have done all these calculations. Okay. They have got gamma 0, that is A1 and A2, and depends that now this one also they found that now depending on this one further they have again, because there are two optimizations. One is that, please try to understand. See, there are here in this case, let me explain this. See, there are two aspects that I have. Now I have to choose my gamma 0. First I am choosing my gamma 0 here, so that my probability of beta will be minimum here in this way. Okay. Otherwise, if I don't choose this gamma 0 at this point, say some arbitrary somewhere, that means if I choose my gamma 0 somewhere here, then what will be my probability of bit error? This portion and this one. Now if you do little bit of calculation, then you will find that when this is my A1 and say this is my A2. Now when A1 and A2 fix, if I choose my gamma 0 at this point, then only this probability of bit error or that probability of error in decision making, that will be minimum. So that's why I am choosing my gamma 0 as A1 plus A2 by 2 that we have studied here, not arbitrarily some gamma dash. Okay, this is one point. So that many times you have studied in hypothesis testing and in probability. So that means that I know that I have to choose my gamma here. Next is another optimization. That now what I am doing, that means yes, this is I can choose gamma. But I can do something that A1 I can shift to this side and A2 I can shift to that side. Okay. Now what will happen? Say I am choosing my A1, A2 here and A1 there. And then I have the same this thing, it will go. And here also something. Here also the same gamma 0. But this area is much less than this bigger areas. Okay. So that's why I am telling that. So that means here what I am doing, A1 minus A2 square by sigma 0 square, that I am into. So that is one I have done, this gamma optimization. That is the probability of bit error. Another optimization I am doing, now I am saying that A1 and A2 I am putting as much as distant as possible. Okay. Now say that now let us talk about bipolar signal. Previously we talked about unipolar signaling where for binary 1 it is class A and for binary 0 it was 0. Now I have a bipolar signaling, that means class A and minus. So that means, so that I explained that this for S1T is class A and S2T is minus, something like this. And so if you can remember, for the same signaling I am doing that 1 0 0 1 1. Okay. So now if I can do something like that instead of S1, that means I am doing this ACT, that reference signal. See, please remember the previous case, my reference signal I have taken it in S1 minus S2 in this way. And here I am instead of doing that, I am doing something like that. Say I have taken a reference signal in this way, S1TA and S2T minus A. And this check, and I am doing a correlation at the both. Now you see that is sometimes I am sending S1, sometimes I am sending S2. When S1 is sent, then this one will be higher. When S2 is sent, then this one will be higher. And finally I am adding it up. Okay, so in that case, and then I am, so that means sometimes ZT will be positive when this one is higher. Sometimes ZT is negative when this one will be higher. So depending on this, and if gamma 0 is some 0, then you will find that if ZT is positive, you will choose that okay, S1T is transmitted. When ZT is negative, then you will say that S2T is transmitted. Now, if you do little and the same thing that 3.13b, I can do something like that also. That I can break it as A1 minus A, Z is Z1 minus Z2. In that way, they have broken it and they do the analysis. And finally, and you know that this is some sort of a, and that means in this case, what was my, this is my S1 vector and this is to my S2 vector. That means rho equal to minus 1. When rho equal to minus 1 is Q of root 2EB by NG. You see that Q of that I run all this analysis. Finally, Q of root 2EB by NG. Now, that in that case, that I have this. Now, if you do little bit of analysis, you will find that it will be gamma 0 will be 0 and all these things because A1 equal to A2 and you will do the analysis and you will get that, you will find that gamma 0 will be 0 in this type of cases, bipolar signal. Okay. please read up to this. And then sometimes what we do that instead of S1T and S2T, sometimes we break this S1 and S2 into a basis function. So that we have studied that S1T, because if you remember that we broke this S1T as summation A or say AJ sin J. Right? Okay, if you can, and similarly S, and we did that J equal to some 1 to n kind of thing, here A equal to 1, and so the same thing you can, instead the same operation you can do instead of ST and S1T, S2T, you can do in terms of the basis functions psi1T and psi2T. Okay, so and you will from there also you will come to the same conclusion. Okay, because why sometimes this is required? Because sometimes in your first, always we are talking about S1 is like this, S2 is like this, or S1 is like this, S2. But there may be some cases say you have some kind of, instead of binary signaling, you have some 2 bits grouped together. When 2 bits grouped together, that means you are sending 0 0 as one waveform, S1T 0 1 is S2T, 1 0 is S3T, and 1 1 is S2. In that case, sometimes what happens that your vectors is like this. Okay, so this is your S1 vector, this is your S2 vector, this is your S3 vector, this is your S4. Okay, in that case, what happens that if you choose this is my psi1T and this is my psi2T, and in all vectors, if you can break in terms of psi1 and psi2, you will find that your analysis will be much easier. So that's why that they do sometimes break it in basis function and all this. Okay. Now there are 2 things. That means, see, these are, let me zoom it. You see, this is a very important part. Okay, this is the bit error probability versus normalized error. Okay. See, this is the bit error probability, and this is my normalized error. Okay. Now, when it is please try to match field reception. In both the cases it is matched field. But in one case it is bipolar, in another case it is unipolar. Okay. When it is unipolar, that means S1T was A for logical 0, or say logical 1, and S2T equal to 0 volt for T small t equal to capital T for logical 0. That means then it is some sort of a orthogonal signaling. Then I am getting a Q of root EB by H. And here you are getting Q root 2 EB by H. Now you see that, and I am plotting in terms of EB by H. That means I am saying, say this is your X, and I am defining Q of root 2x kind of. Here it is Q of root x. Okay. So, and you see, as this one is bigger, okay, for given x, your, for that means for given x, or given normalized signal to noise ratio, that means say normalized signal to noise ratio is say 5T. Okay. Now the probability of bit error, for bipolar signaling, this is 10 to the power something like say -2, but here it is 10 to the near 10 to the power minus. Say it is 10 to the power minus 1.5 or something. Here it is 10 to the power minus 2. So that your depending on your signal, that means see only change you have what you have done. You are how you are representing logical 1 and logical 2. Rest of the things are same. That means depending on the signaling, your probability of bit error will vary. Okay. So this is quite important. Means understand. This is, see, after doing all these things, basic take-home message is this, that these graphs. That if I do instead of unipolar pipe, if I do bipolar, means unipolar bipolar means basically here the thing is that here it is the signal is orthogonal. That means this is S1, this is S2. But here the signal was this is S1, this is S2. Okay, this is in that case when you have something like this, then actually your means your or given SNR probability of feature error will be higher, much lower, or given probability of feature error, your SNR will be much higher for this. Now you try to understand. Just you try to understand. That's very simple. Say I have in this case what I am doing A and 0. That means what I am doing. This is my A and another is this is your S2T. This is S1T. And in this case the same thing, 80 and means plus A and minus. So now for given noise, that means if your noise is something like, say a noise has come and so some A unit of noise, if I have a unit of noise, the 0 volt will be the A unit, the noise value of the, I'm just very super simplistic. If my noise amount is capital A and if it is present for one single time, then actually you have transmitted 0 volt, but actually it may go to plus A. Okay. But the same A, so that means that's a probability of feature. You are transmitted 0, but due to the noise, it is basically it will be detected as some plus. Okay. But the same A amount of noise, so even if it is minus, it will go to 0, or even if it is plus, it may go to 0. Okay. So that means it will not be detected. So that means logical 0 will not be detected as logical 1, or logical 1 will be detected as 0. Or in order to do that, your noise amount should be 2 into. Okay. In order to do the, so that's why that you need more amount of noise. So that means that given, so when the probability of feature error is same, that means your, in order to get the same type of error, you need more noise, because for in this case. Okay. So rather, if I say that in order to, when the SNR is fixed, your probability of feature error is much lower than in this. That means making error in this one is difficult. That means these vector, due to noise, you have to move like this. Then only you can say that yes, it is something. It is a noisy kind of. But here, so that means you have to do, or rather, I can rather, instead of doing this is rather little wrong. Rather, I am saying that means, say I have, this is what I am saying now, that is very important. Say I have like this. Now I have a noise, and this vector has moved to somewhere here. Somewhere. Then okay, this you are okay, that means this is near to this, so you can say no, it is not logical 1, this is logical. So that means you have to move 90. But for this one, say if something like this, if this vector moves somewhere here, very near, say 45 due to noise, then you will detect, oh no, this is not logical, this one. So that means in order to get same error, that means you need more noise. Because of that, your vector will move by 90. Here, your vector will move by only 45. Okay. So that's all. Injust symbol interference I have already taught. Okay, so you can study. You may study from this book. Rather, previous one is better. Don't study from here. But or those things you have studied. This role of factor, value of R in this. So, but please try to study from that one, that the other book that we discussed about this R plus 1 by 2 RS and all this. Then the next class we will talk about this equalization. Okay, that means, and this cosine filter also, Nyquist pulse and all these things we have studied. Okay, square root Nyquist plus. Please study that one. Rather, I will teach the equalization. That means that equalization means that my filter at the receiver side, it should rather take care of the channel induced degradation. Okay. So that means, see, first of all, the comments you see that channel. So that means when you are trying to do the channel, you are trying to mitigate the channel induced degradation. So that means first you have to model the channel. So that model the channel means they are defining the channel characterization. Now channel means that say channel is some sort of a, say this is the channel impulse response HCK and this is my HCK. Okay. Now these are Fourier transform pair and this is my channel's amplitude response or magnitude response and this is my channel's phase response. Okay. So this and that we'll see that this how do we do this channel characterization, and usually that we say that ideal transmission characteristic, we have seen that ideal transmission characteristic of a channel. In that case, that when your bandwidth is minus B2 plus B, that is the B is the bandwidth, then HCF will be mod HCF will be constant. That means your channel for non-distorting channel, say this is your B and this is minus B, this is A, that this is my mod of HF or HF. Okay, C, and what about the phase characteristic is linear somewhere. Something. That means that this must be constant, and this theta CF that is the phase response. Okay, the theta C is that angle of e to the power j theta CF, or angle of this one. That is a linear function of frequency. This is the linear function of frequency, and so that means that amounts to time delay. That amounts to the time delay. Okay, delay and this time delay. And time delay must be constant for, please remember, this delay must be constant, means time delay must be constant for all spectral components. That means 1 hertz, say I have basically a signal composed of say 1 hertz and 2 hertz. Say 1 hertz is say 1 volt and 2 hertz is say some half volt. Now at the DC, this one is moving through a channel. Now you see the basic idea is, let's say I have a signal, I have a 2 component, 1 hertz and another is, this is some sort of, but they say this amplitude is a little less. So I have come, if I just add it up, so something, I don't know how does it look like. There's something like this. Okay, some. Now, basic point is that 1 hertz component will, if it gets 1 millisecond delay, time delay, the 2 hertz component also should get this 1 millisecond. Okay, please remember, then only at the receiver side, both will be adding, because finally it is 1 millisecond, but instantaneously it should add, then only will get this distortionless, the transmitter side, whatever you have seen the signal envelope, the receiver side also will get the same. That means both should reach the receiver side at the same point of time. Then only it will be the same type of x1t plus x2t, or say sin t plus sin 2t will be same. Now when the time, so that means please see that time delay must be constant for all spectral, for 1 hertz, 2 hertz, 3 hertz. Now time delay must be same, means you see that, say this is my 1 hertz, some signal, say some, and say this is my time. Time delay same, that is some time unit same, means here that it is, say it has crossed to 180 degree. Okay. Now for say for some T1, okay, it has crossed 180 degree. Okay. It has moved to, in phase delay is 180 degree. Now for the same time T1, what about that 2 omega component? Sorry. Oh. something like that. That means same T1, your phase will be, here it is, for this one it is 180, for this one it is 360. Okay. So that means, that's why that say that, I am saying that theta CA, phase is linear in frequency, time delay is same, but phase delay for A it is 180, for 2F it is 360. But you just draw this waveform, then you will find it. So that's why that we say that, see, phase delay is linear in frequency, time delay is constant. Phase delay is linear in frequency, time delay is constant for all spectral, time delay is constant in frequency for spectral components. Okay. So these things, this channel characteristics and equalization. Okay, thank you very much. So tomorrow.